Here is an ideal flip-flop, and we want to understand it in terms of being able to draw its timing diagram. If we can draw the timing diagram for a device, then we understand exactly how the device works. The clock comes in here, and here's my clock signal here, and normally clocks are a nice square wave. A flip-flop photographs its input at the rising edge of the clock, and the output records what the last photograph was. So to draw the timing diagram, the first thing we can do is identify where the rising edges of the clock are, because outside those regions the output should just remain constant. Here is the first rising edge of the clock. Moving along, here is the second rising edge. Here is the third rising edge, and we have no more rising edges. We have not been given the initial output value of Q, so we don't know before the first rising edge what value Q will have. So what we can do is we can denote it with a don't know value. This will become useful later on when we study timing. Even for combinational logic, there will be periods of time when we don't know the output due to propagation delays and so forth. To denote a value of don't know, we can basically draw a bunch of x's going between the values of 0 and 1. So in this period here, we don't know what the value of Q is. At the first rising edge, the flip-flop is going to take a photograph of the data line here. And we see for this first yellow line that the value of D is a 1 here. So immediately after, there is an infinitesimal delay, and when we look at cascaded flip-flops, we'll see why this is important. There's an infinitesimal delay, so just after the rising edge, the output Q is going to take the value 1. In between rising edges, the output remains constant. Importantly, even though the input D is fluctuating, the flip-flop ignores this. It only takes a photograph at the rising edge. So the output Q is being remembered. It's not a copy of the input D, it's a photograph of what D was at the rising edge of the clock. We come to the next rising edge of the clock, the second yellow line. Here's the rising edge. We take a photograph of the input D. It's a 0, so that means just after the rising edge, the output Q is going to be 0, and it's going to stay 0 all the way up until the next rising edge. And if we want to be pedantic, then the old value remains up to and including at the rising edge. So it's don't know all the way here. Straight after the rising edge, it takes on the new value. Here's our third rising edge. The value of D is a 1. In between the rising edges, it doesn't matter what D does, the output's going to be constant. At this rising edge, the input D is photographed. It's a 1. Straight after the rising edge, the output of our ideal flip-flop is going to be a 1. And that's the timing diagram for an ideal flip-flop. Here we have two cascaded flip-flops. The output of one goes into the input of the other. We can use this kind of arrangement for at least two different things. Later in the course, we'll understand this can be used as some sort of a synchronizer to help reduce the chance of metastability when crossing clock domains. But for now, we will simply understand it in terms of a shift register. And we will see that the data coming in here gets shifted through this. If you like, this is like a corridor. So in some ways, you can think of this like a long corridor. This is one door. This is another door. We have people walking one by one through the security zone. At the rising edge of the clock, the doors open. One person steps from their current zone to the next zone. And the person that was here goes to here, and so forth. So we shift through this device. So let's now look at the timing diagram to make this precise. Here we have got our regular clock going up and down. At the rising edge of the clock, each flip-flop takes a photograph of its input and sends its photograph to the output immediately after the rising edge. We're treating these flip-flops as being ideal here. We need to know what the input D1 is. I've arbitrarily chosen that D1 is initially a 1, then it drops to 0, then comes back to 1 and stays a 1. This time, let's pretend we are told that we know that initially the outputs of both flip-flops are 0. I have a 0 here and a 0 here, so I can initialize them like that. So, how do we fill in the remainder of this diagram? Well, we just look for the rising edges of the clock. So, here's our first rising edge. This flip-flop here photographs its input. Its input is a 1, and so its output is going to change to be a 1, but just after the rising edge, and we'll see why this is important. So just after the rising edge, I have a 1 here. Do the same thing for this flip-flop. This flip-flop needs to photograph its input, and this is where it's important there was a delay for the output for the previous one. Here's the rising edge of the clock. The input to this second flip-flop is this signal here. The input, you see, is the output of the previous flip-flop. It's taking a photograph at the rising edge. At the rising edge, I kept emphasizing that the output of the flip-flop before has not yet changed at the rising edge. So this flip-flop is going to photograph a 0, and so this guy is going to stay 0. And we go all the way to the next rising edge. Same thing. And order doesn't matter. It doesn't matter whether I did this flip-flop first, then this flip-flop. This time I'm going to do this flip-flop, and then this flip-flop. So at the rising edge, this flip-flop is going to photograph its input. Its input is the output of the old one. And the old one is a 1. So therefore, this flip-flop after the rising edge is going to jump up to be a value of 1. This flip-flop photographs its input. Its input is a 0. And so therefore, the output of the first flip-flop is going to jump down to 0. And the outputs stay where they are until the next rising edge of the clock. Doesn't matter the order. I'll do this one next. Rising edge of the clock occurs here. We photograph the input to the flip-flop, which is a 1, so the output jumps up to a 1 after the rising edge. And because the jump is after the rising edge, it means the second flip-flop, when it photographs its input hasn't changed yet. The input changes after the rising edge. But at the rising edge, the input is a 0, and so therefore the output is going to be a 0. And finally, at the last rising edge, we see that the first flip-flop is going to jump up to a 1, and the second flip-flop is also going to jump up to a 1. So just to be clear, let's now run through this again, but this time just by drawing numbers in the diagram. So initially the input is a 1, corresponding to this part here, and the outputs are 2 zeros. Rising edge of the clock comes along, so this 1 gets shifted along here to be a 1, and this old 0 gets shifted along, and so we have a 0 remaining here. At the next and then in between clocks, the input D1 transitions to 0, so this becomes a 0. And then we wait for the next rising edge of the clock, and then this 1 gets shifted along, so now here's a 1, and this 0 gets shifted in here, so now that's a 0. Then the input D changes somewhere between rising clocks, it's now a 1 again. So at the next rising edge of the clock, the 0 that's here gets shifted along, so I get 0 coming out, and the one that was at the input gets shifted into here, so I have a 1 here. So this diagram is getting messy, but hopefully you see the concept. This diagram defines it precisely, but we think in terms of people. There's one person here, one person here, one person here. At the rising edge of the clock, the person that was here disappears for good. The person that was here moves through the door to here, and the person that was here moves through the door and stays here. This is how a shift register works.